Wow, fast. Fast. Very fast. Nice. Yo, another. Another is here. Welcome back, another. Yo! Saipet! Wait, I think we have new emotes. Wait, I think we have new emotes. BMP... Search? So stupid. Okay. BMP Smart. Oh man. Jeez. Well, that's interesting. Okay. Well, I think that we have two emotes. Maybe there's more. We have to see. Oh, you need the Franker face and BTTV Chrome extension. If you get those two, you'll be able to see all these emotes. It takes 5 seconds. Just go find the Franker face and VTTV extensions for the browser. Yo, Root Guy. Root Guy is probably a family member, given how much they've donated. So I still haven't figured out exactly which family member it is, but I'm still investigating. Okay, let's go. Let's begin with the boring music. Not too loud? Okay, good. A little bit of chill background music for Galois theory. We got 3 things I want to talk about today. It's the chapter in the book is chapter 1, and we'll move on to chapter 2 next week. I'm at pace, so I'm gonna give you your homework, which I can just show you right now. If you want to just write it down before I put it on Canvas. Chapter 1, problems 2, 3, 4, 5, 6, and 13. By the way, I don't completely understand the interesting problem number 12, so if you can figure that out and teach me how that works, that would be nice, but it's not assigned. Just these 6 problems. And due at the end of next week, end meaning Friday, Saturday, or Sunday, we can decide on Discord. Okay, I'm gonna put this up on Canvas after class. All right. Great. Obviously no exam this weekend or this coming week. The exams will start the next week. So let's see. I got 3 things to talk about. 1, 2, and 3. But before we do that, I just want to remind you of the 3 sentences. And as we go, the sentences will come to life, hopefully, and you'll start to see what I mean. All right, here's a picture of Galois, the hero of this whole story. 19-year-old kid. And these are the 3 sentences. Okay? Good. Every time a new number is introduced, you get something called a field extension. That extension has its Galois group attached to it. The more complicated the group, the further away the number is from simple operations like nth root or division, multiplication, etc. expressions. Okay, that's a vague thing. It becomes clearer as we go. You'll understand eventually. Okay, great. Okay. Who's the other guy? I don't know who the other guy is. Anonymous. Yo, wrong class, but welcome. Let's start. Complex number math. Go. Boom. Okay, today's fun though. Complex numbers, then the cubic formula. And then we'll test out the cubic formula on this here example. Let's go. It's a once in a lifetime event to see the cubic formula. All right, this is like a museum trip. It's like one of those field trips. Let's go. Complex numbers. More stuff about complex numbers we need to internalize. Okay, so if you write a complex number like a z, then this is the magnitude. It's the length of the number. Okay, a squared plus b squared square rooted. And so this kind of expression shows up a lot. This one, the square of the magnitude, it's called the norm. And this one's called the magnitude. Okay? Then there's something called the conjugate. This I'll review. I just want to make sure I say the words once. Okay? Okay, when you write the complex number in polar form, r e to the I theta, the theta is sometimes called the argument, but it's obviously not well defined because you can go 2 pi and come back to the same angle. It sort of cycles. But I don't think we'll use the word argument ever, really, in the class. Well, maybe I will later, but at one particular point, but whatever. Okay, so the thing you want to review is when you multiply two complex numbers, the arguments add and the magnitudes multiply. That's the geometric picture of what multiplication of two complex numbers does. Adds the angles and multiplies the magnitudes. All right, that's just something to recall. And so, for example, we can then, using this geometric understanding of a complex number multiplication, you can understand what taking nth roots looks like in the complex numbers. All right, so here's let's look at the particular case of the nth roots of unity. And we're gonna look at the third roots of unity, because then you'll understand every single other case. So you draw your complex plane. This is the imaginary and this is the real. And the number 1 is right here. That number. And you have to ask, like, what complex numbers... Oh, it's slanted, isn't it? What complex numbers cube to 1? So, like, what complex numbers z cubes to 1? Well, if you think about that, the magnitude has to be 1, so it has to be on the unit circle. Because magnitudes multiply, and so gotta be magnitude 1. And its angle has to be 2 pi over 3. So you go 2 pi over 3, and you're gonna get these like these dots. Oh, okay. Has to be 2 pi over 3 or 4 pi over 3 or 0. So the 3 green dots, 1, we can call this omega. Typically, it's called omega. The third root of unity is a little omega. And this is actually omega squared. Also, it's omega conjugate. Also, it's omega inverse. Okay? So that's what the roots of unity look like. They're going to be these perfect regular n-gons inside the unit circle. And there's n of them. N roots of unity, and they kind of distribute like that. Okay, so you get 5th root, you draw the picture. 4th root, you'll get the little diamond square, etc. Great. This is just review. But now think about this. If someone says, I have a complex number, what is its cube root? It's very dangerous to say the cube root of a complex number. It is dangerous. And it's in fact wrong. Because if you do an arbitrary complex number, like way out here, some random z, what do you have to do? You have to sort of, you do polar coordinates and you try to find a cube root of its magnitude, that distance. That's where you're going to have to be. That's radius circle. And then you have to figure out 3 angles that, when you triple them, end up at the angle of z. So at the end of the day, all I want to say is that there are still 3 cube roots of the random complex number z. There are 3 of them, and they're going to be situated 2 pi over 3 angle away from each other, at radius being the cube root of the magnitude of z's magnitude. All right, so there's actually going to be 3 cube roots, 3 like symmetrically situated cube roots. One way of saying this is, if alpha is one of the cube roots, then the other 2 are omega times alpha. Multiplication by omega just rotates or adds 2 pi over 3 to the angle. And then more rotation by omega. These 2 will be the other 2. Okay, and 3 was not special here. Nth root math, nth root extraction is not single valued. Okay? So be careful of the phrase, the cube root of z. There's an issue there. And we're going to see that issue as we move along in this lecture. Okay? Infinity root is a unit circle. That's funny question. I don't know what infinity you mean. But if it's any finite amount of nth root of unity, they'll all become sort of densely packed into the unit circle, but it won't be the full unit circle. Irrational multiples of pi will not get hit if you just look at the nth roots, n being an integer, all infinitely many. Irrational multiples of pi won't get witnessed in that list. Anyway, let's keep going. Okay, so that's I think that's all the complex number math I want to review maybe for you. The homework will have you look at these little omega things and so on. By the way, just while we're at it, for this particular omega, for this particular cube root of unity, we can actually write exactly what this number is using radicals only. This is, I believe, -1/2 plus I times the square root of 3/2. And this one is the other. You can actually write it out explicitly with square roots and stuff. That's because I know sine of these angles and cosine of the angle, right? I'm using this thing. Euler's identity, definition. And I know those two things. Question, here's a question for later. Do we know the exact expressions of every nth root of unity? The 10,000th and 5th root of unity. Not all of them. Do we know the exact expression of them? Good question. That question is answered by a subject called Galois theory. Good, let's go. We'll understand that question later. Do I know them off the top of my head? Hell no. Hell no. I don't even think I know the 7th roots. Is the first interesting case. I don't even think I know them. Yeah, we can try to figure it out. No, I don't know. Do we have explicit kappa? In a sense, you have them for every single one. There's like an algorithmic method for figuring them out. Okay? There's a way. I learned it a long time ago. I can't remember how to do it exactly, but what we will be able to say immediately once we learn Galois theory, especially the third sentence, is that there do exist explicit expressions. The expressions we will know to be, we will know that the expressions exist without knowing the expressions. What a subject. All right, let's keep going. Let's get there. Let's go faster then. Okay, number 2. Our story is the story of solving harder and harder equations. And many people, most people have never seen the cubic polynomial formula. It exists. And I want to show you it. Please understand. I didn't know how to derive it, like, ever. I quickly looked at how to do it about 15 to 20 minutes ago. And I memorized it. Now I'm going to try to execute the derivation of the cubic formula. Okay? Here it is. Okay? Here we go. How to solve for x in ax cubed plus bx squared plus cx plus d equals 0. Get your popcorn and watch me fail. I think I have everything. Let's see if I get it. Okay. There's always a first, wait, x cubed, x squared. Yeah, I got all the coefficients. Okay. First, you simplify it to a simpler shape of cubic formulas, cubic expressions. So what we're going to give you, what we're going to derive is a formula for certain kinds of cubic polynomials, but every other math problem will reduce to this kind. Because if you do something called complete the cube, which in this case is, you do a substitution. Y equals x. First of all, divide out by a. Yeah, just divide out by a. Okay, you do a substitution, which is y equals x plus b over 3. It's called the Chirnhouse substitution. It's like completing the cube instead of completing the square type move. This particular kind of substitution has a mathematician's name attached to it, Chirnhouse. Okay, good. And then you do the thing, and you end up only having to solve this. So solve all riddles of this form, where p and q are now just our two coefficients. It works. Oh, kappa. Good question. We're just going to pretend that right now the coefficients are always complex numbers. Okay? But kappa, in a sense, it works almost symbolically. But we'll have to say what that means at the 2/3, 1/2 mark of the class. When we talk about abstract field extensions. Then we'll say that this works in almost like purely algebraically, where p and q are just variables. Okay, good. Anyway, let's go. So, y cubed plus pq plus... Okay. Here's the genius move that I just memorized from the book. Okay, genius. And the exact genius is somewhere in Italy in 1500s. Okay, all right. The name of this cubic formula is Cardano's formula, but Cardano is not the person who found it. It's the person who published it. Okay, so it's some genius. Okay, you do this. You introduce two numbers, u and v, and you just say, pretend y is, what you're trying to solve for, is the cube root of u plus the cube root of v. You know, just the most obvious substitution that you would do, obviously. Okay, so you do that, of course. And now just collect it. Collect all the stuff. Collect. Okay, let's see here. You gotta do this. You gotta substitute that in. Okay, this I can do. U plus v plus 3 okay, that's the cube of y, and then plus p times y here plus q. Incredible. All right. Okay, now you collect u plus v plus q, like the whole... Okay, you do this. Okay, and then you write down the following. You hope. Then you hope. Now hope. Next hope. So first is pretend, and then the step 3 is hope. Hope that just u plus v plus q is 0, and so you hope that this is 0 and this is 0 simultaneously. System of equations. Let me check chat, make sure they didn't catch a mistake yet. Yeah, I'm going just off of the pure memory here. So just make sure, keep me honest. Okay. Okay, so you hope, just hope. And then through the hope will get realized, and then we'll end up with expressions for an expression for y. Only in terms of p and q. Okay, great. Okay, so now easy. This is easy because you can isolate. Okay, you go like this, and then you divide by the 3, and so you get u plus v equals negative q, and u times v equals. If I mess up here, I'm dead, right? Okay, negative p cubed over 27. Good. Fantastic. I can't believe I got this far. This is a miracle, folks. Okay, next. This part, now it's friendly. Okay, this looks like sum of the roots is one thing, product of the roots is another. This is 3rd grade. Yeah? The little diamonds, you feel it? I don't know if you did that, but okay. So now, look, you do this. U times u plus v minus u times v. That's u squared. But what we're doing is just writing the... Okay, we'll see this trick again at another point. Okay, anyway. U squared is this thing, right? You agree? And then writing that out, you get u times negative q. Plus yes, it's plus. Okay, now the point is, look, where are we? Step 4. Yeah, step 4. We get a quadratic formula. Notice how the cubic formula, at least this derivation, factors through having to be able to solve the quadratic formula. The same sort of thing happens with the quartic formula situation. It's a slightly more sophisticated trick. But what this translates to eventually is that there's a sequence of nice normal subgroups inside of S3 and inside of S4. And the sequence of normal subgroups reflects the deductions of the quartic formula in terms of the cubic formula in terms of the quadratic. It's brilliant that there's an explanation for why the derivation comes through the quadratic formula. It's brilliant. Okay. I can do this. B squared minus 4ac. Okay, there's the book likes to, I think there's a compact way to write this. Okay, it's like this. This is u. And if u is this, then u plus v has to be negative q, and so you can solve for v. And what v ends up being, beautifully, is if u was one of these choices, v will be the other choice. The way you write that symbolically is like this: minus plus. Minus plus is in the context of something else was plus or minus. It's just that choose the other one. That's what's indicated by minus plus. Okay. Oh, you want a quadric of pencils? Just take a break here. This was really advanced, so my students will need a break. Here's a quadric of pencils. Instead of pencil of quadrics, of course. Okay, here we go. Now, we've got u, we've got v. Done. Beautiful expressions. Might as well assume that u is the positive. Okay, might as well assume that u is this one, and that v is this one, therefore. So I'm going to do that. And now we're done, folks. So y equals cube root of u plus cube root of v. Incredible. I actually never did this myself in my life. I mean, I read it and it just glossed over it, but I've never actually done it, like fully performed it like a dance. So this is a special moment for me. I'm choking up almost. What a beautiful formula. All right? So this is Cardano's formula. Notice, plus, minus, times, divide. Coefficients, nth roots. All right? That's called a solution by radicals. Solution by radicals is not, a command by the QAnon. It is radicals means cube roots, nth root symbols. When you put the coefficients in, you can't do natural log of a coefficient or anything. Just the rational expressions in the coefficients. Okay? Solution by radicals. And that's what humanity was trying to find for all polynomial equations of any degree. A solution by radicals. Fantastic. So here we go. This is number 2. I just did it. Again? All right. It's a fantastic derivation. There are others. In the book, you'll see. Maybe in an exercise. There is a derivation using trigonometry. It's beautiful. It's easy again, but how do you think of that? You got to be Italian. This person, this mysterious person, who didn't get credit for it. Yeah, good, fantastic. Okay, now there's something funny about Cardano's formula. Let's talk about that. Now, since my lectures are perfectly, amazingly designed for hours before class, I'm going to go back to something that I mentioned, just a little side remark. The cube root of something. Dangerous. Very dangerous. So let's go back to this formula and see that there's this danger here. What do you mean by this? No, you might not understand what I'm saying yet. Let's apply Cardano's formula to a specific cubic. Let's use it, Let's be applied mathematicians for once. Let's be applied mathematicians. I always get that question. Hey, okay, that's cool and stuff, but what is it used for? Hey? They're just insecure people who don't... Every time, they'll just always ask that question. Well, look, listen, right here. We're going to do an example. Applied math. Here we go. We're going to do, for this polynomial, easy, okay? Just take this polynomial. I don't know why it's so funny, because I didn't truly appreciate this until I read it in the book. Okay. I mean, I knew it abstractly, but where's my copy paste function? Okay, get ready. I copied it this time. There we go. Okay, let's do that. Okay, so what is P and Q? P is negative 15. It's all, oh, notice it's already in Chirnhaus form. There's no quadratic term. And Q is negative 4. Hey, Gath! Welcome. Welcome. Shout out to Gath. Quickly. Go check out Gath. Learn all the organic chemistry. Okay, we're doing some applied math here now. Very applied. Okay, wait, 1 second though. 1 second. By pure genius and rational roots theorem, I don't know if you've learned that, you can see that actually this polynomial has a rational root, 4. And just plug it in. Nice. Okay, but what does Cardano's formula say? It says, okay, it says, oh God, negative 4, so 2. You guys have to keep me honest. Q squared over 4. Wait, 15 cubed? Oh, but 15 is 5 times 3. 5 times 3 cubed. Five cubed. 125 negative 125 plus 15 cubed. Negative 125 plus 4. Negative 121. The only thing that's different here is this minus sign. Huh. Notice this formula symbolically seems to give only one answer, because look, it's just do this and this. But so there's got to be something weird happening, because you expect 3 answers. Where does the ambiguity lie? Exactly when we say take the cube root. Because for each of these summands, for each of these 2 expressions, there are actually 3 options. There are 3 options for both of these things. So let's think about that. Let's think about that in this case, or in any case, but let's look at this particular case as a running example. We have an expression of this form. Pretend alpha was one option for a cube root and beta is another option. So pretend alpha is one of the cube roots of u, this concept of u that we just came up with in the derivation, and pretend beta is one of. Then the end result, one of cube root of blah, not u, but the inside. Just for now, let's just think of that. Well, alpha plus beta is one thing that works, but so does like omega alpha plus beta, omega squared alpha. You don't know which cube root is meant when you just slap a cube root on an expression. It could be any one of 3. And so you get, in this way, a total of 9 possible interpretations of this formula. That's what I should have said. Interpretations of the answer. You get this. You should get 9. Where are they? Oh, yeah. Get a total of 9. Okay? So what the formula is saying is that if you choose the right delicate combination of alpha and beta choices, there's only 3 that work. If you choose them the right way, then you get an actual correct answer. The cube root operation is just a symbolic thing, and you lose information when you just slap a cube root on an object. There are potentially 3 answers, none of which are more important than the other. All right? So what this Cardano's formula is saying is that 4 is some cube root of this particular complex number plus a particular other cube root of this complex number. 4 is writable that way. And Cardano's formula is giving you this garbage instead of just saying 4. And so you'll see a quote in the book in like ancient Italian literature. I think Cardano himself said, yeah, so you get some kind of solution by radicals, but it's kind of useless because in practical real life, you had 4. 4 was a solution. It should have come out in the formula. But it comes out in a completely obscure, weird expression. 2 plus, 11i, 1 cube root of it, plus a particular cube root of 2 minus 11i. Okay, you're right that they add more multiplicity, but if you remember how you're right, they add more multiplicity, but remember that these 2 things, you're absolutely right. Don't the square roots also add to the ambiguity? You're right, but the real ambiguity is caught in the cube roots because let's say that what we mean to put into these 2 square roots are the complex conjugate expressions. So because you see, if this was the plus 1, then this one we mean to be the minus 1. That's the relationship between the 2. And notice if I swap them and keep that opposite relationship, then that's not going to cause an ambiguity. So the ambiguity gets packed into the cube root. Yes, okay? It's a very beautiful things to meditate on. Okay, so if you can sort of cram the ambiguity into the cube root part, and then as long as you specify that what you put into the 2 factors are the conjugate expressions. Great question. Okay. Oh my God. So yeah, this is a correct formula if you choose the right pair of cube roots. Choose correct pairs, correct cube root on one expression and a correct one on this other one. And there's basically 9 options, and you want to make sure you thread that needle. Not discussed. This is beautiful. It's actually beautiful because of the ideas that are captured by it. Yeah. So yeah, 4 is this, where this is to be interpreted correctly. Go find the exact ones. And I think there's a homework exercise that tells you exactly which of the 3 cube roots you need to choose to get to the number 4. Okay? Let me actually show you other interesting answers that Cardano's formula will give you. In case you're wondering, let me now just show you directly from the book now. Okay, let's look. Look at this one. Look at this one. Look at 1.4, which is a homework problem. Okay? Look. Prove without using Cardano's formula that this is 3. Now notice that in this problem, there is no ambiguity in the cube roots, apparently, because both of these numbers inside the cube roots are real numbers, and when you just write the cube root symbol on a real number, they mean a real cube root, the real cube root of that number, the only real number cube root of the real number inside the thing. Okay, so a lot of the possible 9 combinations, they're removing them whenever the inside is a real number. They just mean the real cube root when they put cube root symbol. Okay? It's not garbage. It's beautiful. It's genius. My whole lifetime, I would never come up with a cubic formula. I'm like nowhere close to a 15th century mathematician. This guy whoever found it. It's to be respected. And the point is, there is some kind of radical expression for the roots in the case of degree 3. We just found it. The same is true for degree 4. There's a beautiful radical expression for the roots. Yes, in order to use it and figure out what it's saying, you have to deal with the issue of radical being not single valued, having many interpretations. But the formula is saying, with particular choices, this is what the roots are. Okay? That's way better than, hey, let me just guess and check, and let me try all the complex numbers one at a time. Plug it in. Okay, it's still way better. You got it down to 9 possibilities. And actually, you can whittle it down to even fewer. Read the chapter. Okay? Good. For any general cubic, meaning what you have to do. So let's go through that again. Good question. So the step was this: if you're asked to solve this equation, the first one, general cubic, then first you do a substitution, and you collect all the like terms, and you'll come to an expression like this, and then we solved these kinds of cubics. If that's what you mean by a Cardano cubic, maybe that's the term, I don't know. Then that's what we did. But the point is, it's equivalent to figuring out the general. You'll get the general just by reversing this substitution. All right? Good. No. This particular derivation is important because of the history that it's a part of. Okay, this is as important as a piece of mathematics gets, Kappa. Nothing that you or I will ever do will resonate for as long as this has resonated, because so much mathematics comes out from this particular piece of math. Okay, no other piece of math that you and I will ever create will have this much density. Okay, great. So your calibration is off, my friend. Awesome. Okay, if you weigh a piece of math by how long it resonates for, this is up there. This is like as high as it gets. Awesome. Great. So that's the derivation of the cubic formula. Now go and try those exercises. I will tell you when it's due, or we'll discuss it if you have. I'll ask you when you want your homework to be due, and then we'll set that for next week, the assignment. Yes, Professor Peter, absolutely. Okay, so I'll look at chat now, winding down usual end of class things, but class is officially over. I successfully did the 3 things. Modest aim every class. I only try to limit to 3 things. Complex number review stuff, angles add, magnitudes scale, and then that tells you where geometrically nth roots of numbers should be. Cubic formula, insanely dense, meaning simple, elementary math, but what it represents is timeless almost at this point. And then you try to apply it, and you run into real important questions. What the heck does cube root mean? Which one? Yeah, well, you got to fine tune the 2 cube roots so that you get a solution. All right. And in the book, you'll see ways of narrowing it down to like certain combinations will not even have a chance. But yeah, the others do and form solutions for the original cubic formula. You at least bring it down to checking 9 possibilities. Less than that, but 9 rather than uncountably infinite. So I would consider that progress. All right. But of course, kappa would not here. Kappa 3. And then, yeah, so that's the most maybe explicit math that you'll see for a little bit, I guess. One thing, okay, going back to the 3 sentences, let me say something. This is, you can watch afterwards, it's fine. The genius of Galois and Galois' theory is that, this is comforting to Kappa. It's that one can know that there is a formula without knowing the formula. So amazingly, you can deduce that there must be such an expression, Cardano's formula. Such a thing has to exist without actually going and showing the formula. And that's the power of sentence number 3 in the 3 sentences of Galois theory. In this case, alpha is the root or one of the roots of a cubic polynomial. And the Galois group of that thing will definitely be a simple group. No, an easy group. Either S3 or A3. And those are going to be in a category of groups that are easy and friendly and solvable is the mathematical term. Okay, so that's the beauty of the subject. It gives you conclusions without you having to do what you think is the obvious path towards answering the question. Yeah, I love it. It's every time I think about it again, it's stunningly gorgeous, like this Kummer surface. Okay, let's see. I think maybe only 3 of those 9 possible would end up giving us a real number for an answer. Yeah, I think, yeah. Yes. Correct. Yeah, exactly, Professor Peter. Hey, everyone, all 3 of you, go check out Professor Peter. There are like 4 math professors. 5. Professor Peter is one of them. One of the old meaning, original, like earlier. Yeah. Okay. Anyway. Oh yeah, exactly. But another, I have to say, I mean, I just love this book. Usually I'm very anti-book. I'm very anti-book. But this book is crammed with so much like historical flow that it really makes you understand the progression of humanity's effort to understand these things. I think that's the correct way to learn. Because then you don't end up with these little like perversions like Kappa has, like, oh, it's just this, it's too like this. Yeah, well, if you had learned the history and you feel the weight of history, you would be calibrated correctly. Yeah, that's why I like this book. So, credits. Let's go. Let's go. Kappa, of course. Kappa's calibrated correctly. I just sometimes I'll use a student or any audience member, and I will just twist what they say to serve my purposes. That's what I did to Kappa today. All right, next, we've got great celebrities in the house and mods. All of my mods become celebrities. Is that, what's the causation, correlation? You know? You got teacher's pet, Sheershak. Yeah, I see you. Old friend. Old friend, teacher's pet. Everything you said today was just remarkable. I have to say. Yeah, I stole the teacher's pet idea from Gath. Definitely, shamelessly. But Gath was teacher's pet too. Okay. Oh, thank you, Achilles. And Uno, Dos, Three. And, Indie Rider. And Lambda Overflow for following. Welcome. Welcome to this place. Look who shows up. Look who shows up. Femvox fan. Look what time it is. Credits time. And look, just like clockwork. Incredible. I'm just kidding. I saw you earlier too, so thanks for stopping by. Anonymous, a lot of old students, all my students. All students. Hey, we're gonna have a Discord discussion on when you want homework to be due. I don't want you to be stressed about homework with your other classes. Let's find the best time for people for the weekly homework and exam. Which day you want the weekly exams? Okay. All my students, pay attention to Discord. I flashed the homework earlier in this lecture, so go look at it. But I'll put it on the canvas as soon as I press go offline. That's right. Yo! Meridian John set. Thanks for subscribing. That's not necessary and not encouraged, generally. You must be a family member. Another family member. Like an aunt or an uncle or something. Thank you. Thank you. And that means you went to the top. Can you believe that? There's not enough space here, so I'm going to write it underneath. Wow, incredible. This stream was brought to you by Meridian. Look at that. Okay? Now I can put you up the top. There we go. Okay, fantastic. Let's put that up there. Okay. All right. Hey, folks, we have new emotes, by the way. We all steal stream ideas from Gat, don't we? Yes. Actually, no, but honestly, yes. I need to do the nuance filter. I keep telling myself I need to do the nuance filter. Yes, there are new ones. BMP capital S search, I think. Okay, there's also BMP smart. We just basically went through, we did what Kappa did, which is you go through the videos. Kappa, you okay? Oh, my bad, Kappa. Sorry, Kappa. Okay, there we go. We do what Kappa did. You just kind of go and find funny facial expressions. And so really Kappa gets the real credit for... Okay. All right, Kappa. All right. Let's keep it PG 13. Okay, good. Arbitrary. Yo, didn't see you. Ancient friend of ours here. Like almost gonna, I don't know. No, it's not. End of this semester, it'll be a year. Okay. Vixen, wait, Vixen's here. I hope your semester's going good, Vixen. Though you had it all nicely planned out, if I remember last time. Insane. Okay. I think space economy. Oh, I have a quick question. Is it okay to state an operator in a function with... To state an operator in a function with clear justification and proper mathematics to support it? I don't know what I don't think I understand the question, but this was like 3 hours ago, so you're probably gone. And so I think I can just get by ignoring that now. But I didn't get what you were asking, but I think I vaguely understand the type of question. Good. All right. 1 year celebration party. Okay. Well, this is all great. Fun class. Monday will be fun as well. We'll talk about the fundamental theorem of algebra. So that'll be fun. And other than that, I'll be back at 1:30. 3 hours from now, I guess. With my commutative algebra class. Where we'll talk about some fancy things, I'm sure. Study hard. Yeah. Like you wrote the operation of taking the third root, even though it's in this context wrong. Even though it's ill-defined, right? Not 100% defined. Yeah, maybe that's what he meant. Though yeah, I don't know. Yeah. Right, Kappa. Right. LBMP about the definition of a ring. Yo, what? Who is this? Wait. Wait, who is this? Algebra? What? Wait. Is this someone who changed their name just now? Wait, is this someone we already know who then changed? What a name. What a name. Wait, that's your actual name. That's, oh wait, how long? I can see how long they've been. Let's see. Dude, okay. Your account is from December 30. Who are you, Algebra? Who are you? Tell me right now. Who are you? I know. Do I know you? Are you okay? Don't reveal yourself. Don't reveal yourself. Oh my god. Emmy know there's from history. Yeah, okay. Got it. Thank you. Thank you for yeah. No, it's not. It's not BMP wife. It's not that person. Yeah, look, see? What? Wait. What is that? Wait. Just right. Wait, you just been here the whole time, BMP wife? That's funny. That's funny. Okay, yes, algebra Emmy Noether. Yes. Yes. Okay. Thank you for the lecture. Okay, just tell us more. We should have a thing, no, like hashtag Noether facts or something. And algebra Emmy Noether will just like a bot recite some facts. Oh my. Okay. Let's get out of here. Let's get out of here. Okay. Is there someone you want to go to? Are any of our friends online? Can we transfer you all somewhere? All right, who's on? Oh, I can't read that. Ugh. Who is on? Is Prof. Peter on? Hey, Prof. Peter, are you on? No, it doesn't say. Oh, really? Really? You get Fridays off? Well, that's good. Okay. Okay. Who's on? Is Gath on? Gath. Hey, Gath. None of my friends are on. They're like cool, and they're like the cool kids on Fridays. They get invited to all the parties. Oh, okay. Got it. Wait, Tayo. Tayo's probably not on. Comes on later. Chicken stream? No? Hey, do you guys know EJ? EJSA? That's cool, like space stuff. Space games and like SpaceX rocket launches coverage. You guys know EJ? All right, let's. I'll just dump you in EJ. Okay, we're gonna go to EJ. I'm gonna dump you there, and I'll see you. Yeah. I'll see you at 1:30, or probably some of you. Okay, and I have to learn the material first. All right, good, awesome. We're gonna go to EJ. Okay, whatever. It's Minecraft. All right, thanks for showing up, everyone, and I'll see you next time. Raid now.